Okay, so 2.1, skipping 1.3, 1.4, algebraic domains of functions. We've already been finding domains algebraically a little bit, right? When we've had radicals, when we've taken the radicand and say it was greater than or equal to 0, and we've had a limited exposure to division by 0 when we've had zeros in the denominator. We're going to really look at that on a much deeper level in this section. But before we start looking at algebraic domains and what domains actually are, we need to kind of review functions. And we talked about functions briefly at the beginning of the year. Functions are very special relations. And do you recall why we study functions or why there's so much importance placed upon functions as opposed to non-functions? Well, if you don't remember, you can read this little narrative up above about purchasing pomegranates. Okay? It's kind of a nice little story. Functions help us make sense of the world, right? What do you know about functions? If it was just like word association and I said the word function, what would you say back to me almost instinctively? More than one word even, maybe. Works? Function works. I like that. What did you say? Y equals mx plus b. That certainly is a function. Would anyone say vertical line test? Maybe? No. Someone last week said vertical line test. Okay. You were taught that the vertical line test determined whether a graph was a function or not. And why does the vertical line test work? Because it's a function. Yeah. Okay. Yeah. If it's how does it fail the vertical line test? Let's say that. How does that test work? There you go. The vertical line test fails if the vertical line touches the graph at more than one place at a time. And that's kind of what a function is. So let's define it. It's in a box here. Is everything in a box donuts? No. If you're lucky, you'll have a box of donuts. But in this class, everything in a box, if it's not donuts, is going to be very, very important. Okay? This is very important. This is a definition of a function. A function is a very special relation between two variables, usually x and y, but it could be x and f of x, or it could be z and q, whatever, usually x and y, whereby each independent variable, bold means it's kind of an important word, in the domain maps to, there's another nice word, maps to, goes to, changes into, becomes no more than one dependent variable in the range. Okay, so for any input, which is your independent variable, there could be no more than one output. That's what makes a function a function. And so the narrative up above just says if you go to the store and you buy something, you expect there to be one price. Okay, not two different prices. That would not make sense. Okay, so many things in the world exhibit this relation between inputs and outputs. There are several ways that we're going to be representing functions in here. The first way is the numeric representation of a function. And how would you know that this right here is a numeric representation? It says numeric. Very good. Very good. It also has numbers, yes? This is a screenshot from a calculator. This is the list. This is the first column. That's the second column. And if you see it like this, then that means that they correspond as ordered pairs from left to right. So it's the point 0, 0, 1, 1, 2, 4. If you were to plot those points and connect them, would they pass the vertical line test? Sure, but that's a hard way to determine if that represents a function, right? Plotting all the points and connecting the dots. So how could you tell just from the data that it's a function? It's what? Oh, you actually recognize the function, right? That looks like it's the x squared function. Oh, that's cool. If you can actually look at the data and you know what the rule is that created those outputs and you recognize that graph, then that's cool. But if you don't recognize the pattern of the data and what function generated it, how can you tell otherwise just by looking at the numbers? That's good if you can do that, but there's a different y. That's the reason. Not that there's a different y for each x, but that there is only one x listed. And if you had an x listed twice, it better be the same number, which we wouldn't need to repeat it. So the x values do not repeat. That's how you know. 0, 1, 2, 3, 4, 5, 6. It doesn't really matter then what's in y1, the column. There could be these numbers here, or it could be that they're all 9s. What if all the column in y1 were 9s? Would it still be a function as long as these x lists were the same? Yeah, it would graph as a horizontal line. If all the y values are 9, it's a horizontal line. Does a horizontal line pass the vertical line test? Heck yeah. What if like a 6 had no number there? What if the 36 was gone? Would it still be a function? Yeah, coming back up here, it says this little key part right here. Each input has what? No more than. So that really means less than or equal to one output. Is 0 less than or equal to 1? Yeah. So it could be that an x value has no output. That doesn't prevent the ones that do have outputs from being a function if there's only one output. We would say then if there was no output that that x value is actually not in the domain. And we'll talk about that here in just a second. Okay, so another way that we can represent a function is graphically, right? And that's real easy. If you have the graph, you just do the vertical forearm test, it passes, right? If that vertical line does not touch the graph in more than one place, it passes and it's a function. And then we have the algebraic or analytic way to represent a function, which is something like this. And how could you spot a function from the equation? That one's not as straightforward, but there are still several right answers. If you looked at that, how would you know that that's a function? It says f of x. Yeah, first of all, look at the notation. If you see f of x or g of x or h of x, that's function notation. You don't use function notation unless it's a function. So that's a giveaway. But what if that was just y equals x squared and it didn't have the f of x? Could you still spot that as a function? How? Why? It has two variables. There's a relationship between them. What if I looked at y equals 5? That only has one variable. Is that a function? That's a horizontal line. So it doesn't necessarily have to have two variables. It has y. Uh-huh. Can I reverse them? Can I reverse the variables? I could. So, but then how would we know it's not a function? If you graphed it? Yeah, well, you might recognize x squared, okay, like Michael did from the data, and you say, oh, that's a parabola. It passes the vertical line test. But there's going to be another way to tell from the equation. You're going to see equations that you don't recognize, and there's going to be y's all over the place. So here's kind of a quick, easy way. That doesn't always work, but for the most part it does. If you look at the exponent on your y, it's a what? A 1. For the most part, that exponent on the y will tell you how many y values are associated with any given x value. Okay? So that means that any given x value will have how many y values associated with it? 1. And is that okay? Now, not all x values might have or wouldn't necessarily have one y value, but no more than 1, right? So that would work. That's one way to do it. We'll talk about another way here in just a second. But before we do that, before we start looking at some examples, I do want to kind of create an analogy that y'all probably seen before regarding a function. And you don't have to draw this if you just want to listen. This is like the little function machine that appears in a lot of Algebra 2 textbooks. You've probably seen something like that before. Okay? I like to think of this as like a wood chipper. Okay? And you have this little port at the top, which is going to be your input. Okay? And you put something in, and f of x is a rule that changes your input possibly and then spits out an output. So for us, our inputs are usually the x values, right? And the outputs are usually the y values. Yes? Now, what can we put into a wood chipper? Think of a wood chipper. What can we put into a wood chipper? Wood, logs, right? We can put in logs. And if you put in a log into a wood chipper, what do you get out? Wood chips? Every time? Sawdust sometimes if you put in like a wimpy log, right? But you always get one thing out, right? Never will you put in a log, and you can't put the same log in twice, I guess, right? But let's say you have, that would be cool. Let's say you have two identical logs, right? They're identical twin logs, okay? They're from the same egg. And you put in the first log and you get out wood chips, and you put in the second log, are you going to get out like banana pudding? I wish. That'd be cool. Like in your dreams, right? Maybe if you like banana pudding. It may be a nightmare if you've had bad experience with banana pudding. But that doesn't make sense. It doesn't happen because one input is going to have one predictable output. Doesn't make sense, right? So can you put other things into a wood chipper besides wood? Sure. Like what? Grapes. Okay? If you have a giant party and they want like mashed grapes and you have a wood chipper on hand, you can put them in there and you can have mashed grapes very easily. Shredded grapes, whatever. Yeah. But if you put in grapes, you don't get out wood chips, right? You get out shredded grapes. It's very predictable. One output. What else can you put in a wood chipper? Potatoes, right? Potatoes. And you get out potato chips. Healthy. You put in cheese. Someone last week said cheese. You get out grated cheese, right? If you're having a nacho party, maybe that's the way to go. The key is that you could put anything in a wood chipper that is within your grasp, right? Within your realm. Yes? Or within your what? What's another word? Within your, it's Harry Potter week, within your domain, right? You can put anything into a wood chipper that is within your domain. So the collection of all inputs are called the domain. And of the things that are within your grasp or within your domain, you can choose independently, right? Like you're staring at the fridge, you got grapes, you got cheese. It's your choice which one to take outside and put in the wood chipper. So you have free will, free choice, or what we say, you can do it independently. So the x value is going to be the independent variable. The collection of all the independent variables is called the domain. Now, your outputs, let's see. Depending on what you put in, you get out a whole variety of outputs, yes? What's another word for variety? You get a whole range of possibilities. Range, there you go. So the collection of all outputs are called the range. And of course, as I've already said, what you get out so totally depends upon what you put in. So these are called the dependent variable. Okay, they're all kind of associated with each other. Now, does everything you put into the wood chipper have an output? No. What if you have like a giant metal rod and you stick it in the wood chipper? It's going to break the wood chipper and you get no output. So would it be fair to say then that you didn't read the manual on the wood chipper? Because it probably says, don't put metal rods in wood chipper, right? Even if you're having a shredded metal rod party, find another way to shred that metal rod. Do not put it in the wood chipper. You would say then maybe that the metal rod is not in the domain of the wood chipper? Maybe? Even though it's within your grasp? You're not going to dare put it in there? Would that be safe to say? Maybe? Sure? Okay. Even if you have your safety goggles on. So not every input's going to have an output. Not every input is going to have an output. Some things break the function, like metal rods. Not every input's going to have an output. But if there is something that comes out the other side, it's predictable based on what you put in. And there's only one thing that comes out the other side. Right? Not wood chips one day and vanilla pudding the next. Very good. So, what we're going to do now, actually, before I do that, let's talk about another way you can represent the data. If it's not in table form right here, that's what this note kind of says. You can actually have the same numbers listed as a set, notice the braces, of ordered pairs. But it's almost just as easy to determine if this is a function, right? Because you're just looking at the x values. And if you have an x value that repeats, then you have a log going to wood chips and banana pudding at the same time. Okay? Questions? You're ready to do some problems. I know I am as well. So let's look at example 1. We're going to determine if the following representations are representations of functions. Now this is an adaptation on a numeric representation. This is called a mapping. We have a list of x values and y values which are title, domain, and range, but they may not be. We'll decide if in fact they are. We don't associate them straight across. It's not necessarily the ordered pair -3, -6, -2, -1. The arrows kind of show you where each of the x values go. It's a mapping. So look at this one right here and decide, does this mapping, this relation, represent a functional relation? Yes. Emphatically yes. Bless you. Why? Right. Let's just say that each x value, and I'll use the word maps to only one y value. And that's kind of a complete sentence there, yeah? Very good. Could we then figure out what the domain is? It doesn't have a name, so I'll just put D. Can we figure out what the domain is? Is that truly the domain there listed in the left column?
No.
That's not the domain?
There could be more.
There could be more, right? There could be more. It might not be the entire domain, but if I told you this represents the function in its entirety, you're right, there could be more. Let's list the domain that we actually have. We actually can, in fact, just list them, right? It would be like a roster. It's a short list, -3, -2, -1, 0, and 1. That could be the whole list there. And then the range, what would the range be? -6, -1, 0, 3, and 15. Do those have to be in increasing order if it's a roster, if it's a list of the complete set? No. It's only if we're trying to develop a pattern where we need the order to matter. Okay, very good. That was pretty easy. Letter B. Woohoo, look at that. -6 is looking pretty popular, right? She has her choice of dates for the homecoming bash dance on Saturday night. Everyone wants to go with -6. Is that a function?
Yes.
-3 goes to -6, -2 goes to -6. They all go to -6. If you were to plot those points, -3, -6, -2, -6, -1, -6, and connect the dots, it would make a what? It would make a horizontal line. Does the horizontal line pass the vertical line test?
Yes.
Yeah, we already said yes. So this is yes. You can have the y values repeating. The y values can 2 times the x values. That's legal in a function. The y values can not only 2 times, they could quintuple time or infinite time those 4x values. But the x values, they're not allowed to 2 times. They have to be faithful and monogamous to only one y value, or they can be celibate. They can be by themselves and have no output at all. Okay? So this is yes. Yes. Okay. Yes. We'll say that each x goes to, that's another way to say the map, goes to only one y. Very nice. I'm glad I wasn't needed in that transaction. Thank you for hearing that. All right. What's the domain here? Can we list the domain? All real numbers? Well, based upon this mapping, there might be, if it's truly a horizontal line, it would be all real numbers. But in this case, it's just those numbers there, which I guess we could say is a set of all x such that -3 is less than or equal to x is less than or equal to 1, such that x is an element of the integers. Can we do it that way? Would that work?
Yes.
That works, right? That's, I guess, the more fancy way. We could just list them again as well. But that does work. That's a good review. And what about the range? -6. It's a very short list. Okay. All right, moving on then. Letter C. Function, yes, no, maybe so.
Yes.
I got a yes, got a maybe so. Anyone got a no?
No.
It's actually no. Why? Yeah, 1 kind of ruins it. 1 is 2 timing, and the credo of function is x's can't 2 time. They can 1 time or be alone, but they can't 2 time. So no, comma, x equals 1 maps 2, 2, 2 different 2's, 2, 2, y values. Okay? Not good. If you were to plot the point 1, 0 and 1, 15 and connect those dots, it would make a what? Vertical line. Does a vertical line fail the vertical line test?
Yes.
Horribly, yes. Okay, this last one here. Yes? You're right, yes. Okay. And again, each x goes to 1y. Each x to, but I'm going to say to no more than, which is slightly more significant here, no more than 1y. Because what's happening with the 16? It doesn't have an output. That's like the metal rod that's laying next to the wood chipper that you know not to put in. There's no output, okay? So this is kind of a misnomer. 16 then would not be in the domain. Okay, if you were to list the domain here, even though the column says domain, the domain is just -3, -2, -1, 0, and 1. 16 is not in the domain. Okay, just like a metal rod would not be something you'd want to put in a wood chipper. So if we scratch this out, because it's not truly the domain if 16 is in the list, there is something it is equal to, and you don't have to know this, but it's kind of nice to learn new terminology. It's in what we call the pre-image. Okay, it's kind of a collection of candidates for the domain. It's like you have guys sitting around, I hope they pick me for the domain today. Oh, shucks, I didn't make it. Okay, it's in the pre-image. The domain is a subset of the pre-image. And then the pre-image then becomes the image, and there might be guys hanging out in the image that didn't come from the pre-image. They just were born there, and nothing took them there. So the range then would be a subset of the image. So it's kind of like in set theory, we talk about this kind of stuff. You don't have to know that, but just realize that 16 is not in the domain. Not every X value has to have an output, but if it does have an output, one and only one. Got it? Pretty easy? Okay, very good. Very quickly then, let's just talk about these set of ordered pairs. It's another numeric representation. Function, yes or no? No, right? Why? Right. X equals 6 goes to 1 and to -5. I'm not going to write it out, but you could say that. No, X equals 6 maps to two different Y values. So that's no good. What about this one over here? No. Right, X equals 5. So no, same reason. Same reason. X equals 5 goes to two Y values. So you can have repeated Y values, yes? Repeated Y values are fine. No repeated X values. No repeated X values. Okay, so I think we got that done. The numeric is not that difficult to represent or to identify a function, but it is not by far the easiest way to identify a function, because example 2 is even easier. If you happen to have the graph of a relation, you can determine very quickly if it's a function, okay, because you have the vertical line test, and you can just like visually inspect it from left to right. So we'll do these quickly. This looks like a parabola. Does it pass the vertical line test? Yes. I'm not going to write yes. I'm just going to put a check. Check for yes. Yep, function. Got it. Good. Here's a tipsy parabola with balance problems, huh? Function? No. Okay, no. Fails the vertical line test. So again, notice that at this X value, there are two Y values associated with it. Does every X value on that graph have two Y values associated with it? Every single X value except one of them, which is the vertex. So again, not every X value has to have two or more Y values. But on any graph, if there's just one X value that is 2 times a Y, it's guilt by association. They're out of the domain club. All right? I didn't erase this from last period. I hated to give it away, but yeah, close your eyes. Pretend it never happened. Hey, that brings us to example C. What do you think about example C? Yes or no? Function, vertical line test, pass?
Yes.
Yes, it does. Very good. Now, we're going to be studying these types of graphs later on in the year. This is a polynomial. Does anyone want to make a guess as to what the degree of this polynomial could be? 7. I like the 7 because it's an odd number, but 3 is a better odd number in this case. This is actually a third-degree polynomial. You can tell because it's a pretty straightforward curve. It has 3 x-intercepts. The maximum number of x-intercepts is going to be the degree of the polynomial. You can also look at the number of relative extrema, the turning points. That's what we call those. If you take those maximum number, which is 2 in this case, and add 1, you also get the degree. Okay, so we'll study those. There's a whole unit on polynomials later. One last question to see if you happen to know this. It's going to be an x cubed. Does anyone know anything about the leading coefficient of x cubed? Is it going to be positive or negative? It's going to be negative. Why? Oh, yeah, it comes in with the negative slope. That's one way. That doesn't work for x squared, right? X squared that's negative comes in with a positive slope. But you're right, it is negative, and here's how we're going to tell later on. If you look at the way the graph always exits on the right, you'll be able to tell the sign of the leading coefficient. If the graph exits the bottom on the right, it's going to be negative. If the graph exits the top, it's going to be positive. Just like negative x squared, right? It exits the bottom. We'll get all that later on. But it is a function. Right now you're looking at that. Yep, vertical line test. It is a function. All right, picking up the pace here a little bit. D, function, yes, no?
Yes.
Yes, sure is. E.
Yes.
Yes, that actually looks like it's part of a circle. What if I had the other part of the circle?
No.
Oh, that's a horrible looking other half. That would fail as a function, right? Everyone spot the circle in the worksheet? A throwback review question? Yeah. We knew that was a circle because we looked on the key. But if you didn't look at the key, you might have recognized it was a circle because this is a form of a circle. If you have x squared and y squared, then the center is going to be at 0, -5. Okay, because this is x minus 0, y minus -5, and this is the radius squared, so the radius was 2. Okay, you had that in Algebra 2 when you studied conics. I just put that in to see who remembered it. But circles are not going to be functions. Now, is there a way to spot that from this equation without looking at the graph? How? Very good. If you remember what I said a little while ago, if you look at the exponent on the y, and if you expanded that out, you'd have y squared plus who cares for now? You'd have y squared. And the exponent's 2 on the y, which means for every x, there's potentially 2 y values, so that wouldn't be a function. Okay, what about f?
Yes.
Yes? What about at on the y-axis? Yeah. It's closed at the top. We'll accent it there. But it's open on the bottom. So when you put a vertical line on the y-axis, there is no sharing violation. There's only one. Okay. This function is not created from a single equation. This is called a piecewise function, and we'll be using these quite a bit this year. It's kind of like a centaur, you know, that's like a half horse, and at the torso it changes into a creepy man in the shower selling Old Spice soap. Right? Have you all seen that commercial? These are functions that are part one graph and then part another graph, and they don't always change at the torso. In this case, it's one line that changes into another line, and they change at x equals 0. So we'll be working with those quite a bit. Now, what if it was the same graph except it was closed at the bottom also? Then it would not be a function because now x equals 0 would have 2 y values. What if it was open on both, top and bottom? Would that be a function? Yes, but now x equals 0 would not be in the domain because there's no y value associated with it. Very good. Okay, y'all got it. So the original verdict was, yes, it's a piecewise function. All right, so graphs are easy, right? Piece of cake graphs. What we're going to be working for then is how can we spot from the equation, which is a little more fun, right? And it's impossible to even say function without saying the word fun. So built right into the program here. So let's look at this one right here. 3y plus 5x equals 7. That's an equation. There's no f of x in it. Is that a function? Would that graph pass the vertical line test? Yes. Yeah. How do we know? It's y to the first, right? Y to the first. So yeah, this would work. If you were to solve that for y, what would you get? Let's try that. 3y equals negative 5x plus 7. You get y equals negative 5/3 x plus 7/3. And you recognize that as an equation of a line in slope-intercept form. You can always graph lines the way you learned in Algebra 1. You can put it in slope-intercept form, go up to 7/3 on the y-axis, put a dot, and then these are the instructions for the other point. Go down 5, right 3, down 5, right 3, and put another point and connect them. Okay? Now, this is pretty important because if you are not comfortable looking at the exponent on y, and sometimes it can be a little tricky, here's another criteria for determining if it's a function or not, and it's right below here. Can you solve the equation exclusively or explicitly for y? Can you solve it exclusively or explicitly? When I say explicitly, it does not mean can you solve it without cussing because you're frustrated. Okay, explicitly means that you have y equals, and then there's something on the stuff that has no y's in it at all. A single equation with no y's on the other side. Okay. Well, we just did that, right? We had y equals, and on the right side, there were no y's. So, yeah, that's another way to determine if it's a function. So, let's compare that with this one here. X squared plus y squared equals 10. Is that graph going to be a function past the vertical line test? No. Two ways to tell. You got a squared there. That's no good. I'm going to keep teaching over it. If I try to solve that for y, I get y squared equals 10 minus x squared. And if I solve for y by taking the square root, I have to do what? What kind of square root? Plus or minus. Okay? When you do plus or minus, you're basically saying for this x value here, you're going to have two y values, right? One positive and then one that's negative. And that doesn't work. If you were to sketch, the square root of 10 minus x squared, it might look like that. And then what would the negative version do? Based on transformations, if you put a negative in front of a function, it does what? It would reflect it across the x-axis. And we'd have both of them, which automatically would fail the vertical line test. Okay? So, we didn't get that far. We'll start with number 3 tomorrow, but we'll move a little bit more quickly tomorrow. No quiz tomorrow, but we will warm up still. We don't want to start cold. And we'll go through these and determine if the equations then represent functions. Okay?